This is Radhika. I'm going to discuss about power electronics. Under that, we are going to discuss about the class E and class F commutation. In last classes, we discussed about the class A commutation, class B commutation, class E commutation, class D commutation. Today we are going to discuss about the class E and class F commutation. So, in previous classes, we discussed class C and class D commutation. So, today our topics are circuit diagram of class E and class F commutation, working and waveforms of class E and class F commutation. First, we are going to discuss about the class A commutation. So, actually, what is class A commutation here? In this commutation techniques, a reverse voltage is applied to the conducting thyristor from an external pulse generator. So, it is called external pulse commutation. Here, in this we call here the techniques, a reverse voltage is applied to the conducting thyristor from an external pulse generator. It is called the external pulse commutation. Pulse generating transformer is so designed with very small air gap between the primary and secondary windings to avoid saturation. Here in this, this is the circuit diagram for class C commutation. In this, a reverse voltage is applied to a conducting thyristor from an external pulse generator, so it is called external pulse commutation. Pulse generating transformer is so designed with very small air gap between primary and secondary windings to avoid saturation. Once the thyristor is triggered, current flows through the load resistance and the pulse transformer. When the commutation of thyristor 1, the thyristor 1 means here the SCR1, this is the SCR, the thyristor. When the commutation of thyristor T1 is desired, the capacitor voltage reduced to 1 volt and a high frequency pulse of voltage, the voltage V means source voltage, here it is the E, is applied from the pulse generating transformer primary, which in turns induce a voltage at its secondary. This voltage appears as a reverse voltage across the thyristor, and hence the thyristor gets turned off. Once the thyristor is turned off, the load current decays to 0. So, that will be shows in waveforms. So, in this class C commutation, so in this external pulse source is used for commutation. The transformer designed with sufficient iron and air gap so as not to saturate. It is capable of carrying the load current with a small voltage drop compared with the supply voltage. So, this is the diagram of class E, and when SCR1 is triggered, current flows through the load and pulse transformer. The current will be flow from SCR to load transformer, pulse transformer. The turn SCR of a positive pulse means to turn SCR1 of a positive pulse is applied to the cathode of the SCR from an external pulse generator via the pulse transformer. And also the capacitor. In this diagram, the capacitor C is only charged to about 1 volt, and for the duration of the turn-off pulse, it can be considered to have zero impedance. Thus, the pulse from the transformer reverses the voltage across the SCR, and it supplies the reverse recovery current and holds the voltage negative for the required turn off time. So here in this, this is the class F commutation. So in class F commutation, this commutation technique is also called as natural commutation or line commutation. So in this simple commutation circuit of line commutation during positive half cycle of input voltage, the thyristor conduct and the source voltage will be transferred to load. During the negative half cycle, the thyristor gets turned off due to reverse source voltage, and its current is less than holding current. It is necessary that the turn off of thyristor is less than duration of negative half cycle, or the duration of negative half cycle must be more than the turn off time of thyristor. The applications of class F commutation, it will be used in phase controlled rectifiers, line commutated inverters, AC voltage regulators and step down cyclo converters. So here in this line commutation, in class F commutation, circuit is a AC line commuted circuit, and if the supply is an alternating voltage, load current will flow during the positive half cycle. So this is the diagram for class F commutation. It has the 4 thyristors and 1 freewheeling diode. In this class F commutation, with a highly conductive load, the current may remain continuous for some time till the energy trapped in the load conductance is dissipated. During the negative half cycle, therefore, the SCR will turn off when the load current becomes zero naturally. The negative polarity of the voltage appears across the outgoing SCR turns the voltage persists for the rated turn-off period of the device. The duration of the half cycle must be definitely longer than the turn-off time of SCR. So this is about the class F commutation, and here in this commutation, so this is the last topic in power electronics devices, but here this is the last topic in first chapter. Before going to this to end this chapter, we are going to discuss some applications of SCR. So here applications of SCR, the following few applications. It is the few applications of SCR. Light dimmers in home and theaters. The SCR are used in few circuits that are light dimmer in home and theaters, power supply for aircrafts, space shuttle, and satellites, and battery charger circuits in AC and DC drivers in rolling mills, paper mills, textile mills, cement mills, etc. So here switch mode power supply SMPS and uninterruptible power supply UPS for computers and other electronic equipments. Solid state controllers for home appliances, electric traction vehicles such as tram cars, trolley buses, subways, electro locomotives, etc. High voltage direct current HVDC transmission system. Power control in metallurgical process using electrothermal process such as electric arc melting, arc welding, induction heating and melting resistance heating, etc. Power control in chemical processing using electrochemical process such as electrolysis, active power filters and reactive power compensators in power system, high voltage supplies for X-ray generators used in X-ray machines, high voltage supplies for electrostatic precipitators used in chimney to separate suspended particles from flue gases to control the pollution. Static circuit breakers and also the SCRs will be used in transformer tap changers and static contactors in industrial power system. Solid state controllers for mine winders, cranes, elevators, lifts, excavators, etc. And also the GTO SCR will be applied for used in electric traction means railways because of lesser weight, used in adjustable frequency inverter drivers, and also it will be used in rolling mills, robotics and machines tool to obtain high performance. So here the applications of DIAC, it is used as triggering device for TRIAC and light dimming circuits, heat control devices, speed control of universal motors, and the applications of SCR is speed control of single phase induction motors, series motors, and electric fans, heat control devices, and also used in liquid level control devices, illumination level control devices, used in industries and uh, domestic purpose. And also these are used in phase control circuits, power switching circuits. And also the IGBT also used in, it is used in choppers to convert DC to DC power supplies, in UPS systems and inverters, AC motor drives, harmonic compensators, SMPS means switch mode power supplies, traction motor control and induction heating. And also lastly the laser will be used in, it is used in HVDC electric power transmission, static VR compensation systems, light activated flash units, relays, phase control and computer systems, and also it is used in alarm and logic circuits. So this is about few applications of SCR, DIAC, TRIAC and GTO SCR. This is the last topic in these power electronics devices. Now we discussed about the class E and class F commutation. Now we can watch the one YouTube video for class E and class F commutation.
Good morning, all of you. In today's session, we are going to revise the turn on and turn off methods of SCR. Among these methods, we have to briefly revise the class E commutation of a SCR. So, in this discussion, class E commutation is one of the forced commutation method to turn off a SCR or a thyristor. It means we know that commutation means in commutation we are turning off a SCR. Now in this turning off a SCR, so commutation means to turn off a SCR, and these turn off methods, they are classified into two categories. First category is natural commutation, second category is forced commutation, and under the category of forced commutation there are subcategories of class E commutation and class F commutation. These are the two subcategories. In this category, in this subtype, external pulse or external current signal is used to turn off a SCR. So, because of this reason, this class A commutation is also called as external pulse commutation. Listen once again. In this commutation technique, external pulse or external signal, it is applied. So for this purpose, this method is also known as, this method is also called as external pulse commutation. This external pulse, it is obtained from, it is taken from another voltage source. It is taken from separate voltage source. So as you can observe the circuit diagram for class E commutation. In this class E commutation diagram, it consists of voltage source, which is denoted by E. E is voltage source. Capacitor C, here SCR, or you can call it as a thyristor, and at this stage transformer is used and it is a pulse source of pulse, or from this source the pulse signal is applied. Now because of this arrangement, what will happen? Pulse transformer, it is used to apply the commutating pulse. As you can see, this transformer is connected to cathode terminal of a SCR. As it is connected to cathode terminal of a SCR, so when we apply, or when we make use of this transformer, then what will happen? Voltage at secondary of pulse transformer, it will appear across thyristor T1 as a reverse voltage and it will turn it off. This is the concept of class E commutation. Voltage at secondary of pulse transformer. So now look at this transformer. It is having two windings. We know that transformer have two windings. On this side, on right hand side, we consider as primary winding, and on left hand side it is having secondary winding. So what will happen? At this secondary winding, voltage will appear. Voltage at secondary of pulse transformer appear across this SCR, and it will act as a reverse voltage. This voltage will act as a reverse voltage, and because of this voltage, this SCR will get turned off. Now consider another alternative representation of class E commutation. Now in this commutation, in this diagrammatic representation, EDC, or it is a DC supply, voltage supply. C is capacitor, SCR T1 is 1 SCR or a thyristor, RL is load resistor, IL is current flowing through this resistor. This is pulse generator, and it will generate a square wave type of signal. This is a pulse transformer, and as you can observe in this diagram, we can turn off a SCR by using this arrangement. In this arrangement, IG1 is nothing but get current of this SCR. When we apply IG1 at this instant, so because of this, when IG1 is applied, IT is value of current. This IT will having some value. Current will flow through the T region, or current IT will flow. It is denoted by this pulse, and after some time, when T off is applied, or when ET1 is applied, ET1, because of this application, EP is nothing but pulse signal. When this pulse is applied, you can observe that the value of IT is 0. Value of current IT is 0. So the transistor, it will turn off. SCR T1, it will turn off. Current flowing through this SCR T1, it will be 0, and voltage, some voltage will appear at this instant. During this instant, there will be some value of voltage across this SCR. So from this waveform, it is clear that we can conclude that after applying the pulse signal, current through this SCR is 0. As current through this SCR is 0, it is commutated, means it is turned off because of this. Similarly, another type of commutation is class F commutation. In this commutation technique, in class F commutation technique, first observe the circuit diagram of this commutation technique. In this circuit diagram, AC source voltage is applied, AC signal is applied from left hand side. It is connected to SCR T1, it is connected to SCR T1 and resistor RL. These are the three major components of this commutation technique. AC supply, AC signal, it is denoted by this sinusoidal symbol, this waveform symbol. Next component number 2 is thyristor T1, and third component is resistor RL. Now In this commutation technique, the concept is simple. In class F commutation, it is AC line commutation method. AC lines means AC means alternating current. AC signal is applied. So it is AC line commutation method. As the supply is alternating voltage, load current flow during positive half cycle. During negative half cycle, SCR will turn off. We know that a sinusoidal waveform, any sine waveform, it is having plus half cycle and negative half cycle. Any sinusoidal waveform, it is having positive half cycle as well as negative half cycle. So, during negative half cycle, the SCR will turn off, and during positive half cycle, the SCR will be turned on, or you can say that load current will flow during positive half cycle. So in this method, it does not require any additional commutating element. As you can observe in this structure, there is no external element is necessary for commutation. This method is used in all controlled rectifier circuit. This commutation method is used in all controlled rectifier circuit. Now look at the waveforms of this commutation method. As you can observe, the waveform, it consists of 4 components. On x-axis, time t is plotted. To draw a waveform for class F commutation, we have 2 axes, x-axis, vertical axis, and y-axis, horizontal axis. On y-axis, on this horizontal axis, time t is plotted. Time, we assume that initially time t is 0. We have assumed that initially time t, value of time t is 0. And Ig1 means I stands for current, G1 means gate current. ES is nothing but applied voltage. IL is current through this resistor RL. L stands for load, I stands for current. ET is voltage across this SCR T1. ET1 or ET is the voltage across this value. Now initially what will happen when we apply a trigger pulse, when we apply value of Ig1 get, when we apply current to gate terminal. So because of this, what will happen? Current IL will flow through the SCR. Observe this value of current IL. It is having some positive value. It is having some value. It means current flows through this SCR. Now you can observe that during this half cycle, this is a positive half cycle, this is a negative half cycle. During positive half cycle, current flow through the SCR, and during negative half cycle, this is a negative half cycle. It is called as negative half cycle because it is below this x-axis, it is having the negative region. So during negative half cycle, value of current is 0, value of current IL is 0. It means no current flow through the SCR, no current flow through the SCR. So SCR is automatically turned off. SCR is automatically having 0 current value. So this is the process to turn off a SCR. This is a method to turn off a SCR. Now in this method we have to take one precaution. While listen carefully, in this method when we turn off a SCR or when we commutate a SCR, at that time for successful commutation reverse voltage must be applied for a time longer than the turn off time of SCR. Now reverse voltage means what? This is negative region. This is called as negative half cycle, or it is also called as reverse voltage. So this voltage, its time duration, it should be longer than turn off time of a SCR. The duration of this region or timing for this region, timing of reverse voltage, it should be greater than turn off time of a SCR. Then only this method will be successful. If reverse voltage is less than turn off time of SCR, then this method becomes unsuccessful. Commutation will not take place. Commutation will not happen during this. Now, in summary, we can revise both the commutation methods, class C, class F. These are the simplest commutation method we have seen till now. In parallel, you have to draw these two diagrams for class C commutation and class F commutation. This is simple diagram of class C commutation. So in summary, we can say that by using these two commutation methods, we can turn off a SCR. By using these commutation techniques, we can turn off a SCR. Last point about this discussion is homework question.
So we watched the E and F commutation in YouTube video. So this is the last topic in power electronics devices. Already in previous classes, we discussed about the introduction of power electronics devices and the thyristor family. In under thyristor family, we have the 15 devices that are SCR, track, diag, GTO SCR, SUS, in silicon unidirectional switch, silicon bidirectional switch, silicon controlled switch, asymmetrical SCR, light activated SCR, reverse conducting thyristors, static induction thyristor, mass controlled thyristors, programmable unijunction thyristor, and Shockley diode. And also we discussed about the symbolic presentation of thyristor devices, circuit symbols, and construction details of SCR, working of SCR, and also we discussed the VI characteristics, of thyristor, gate characteristics of SCR, SCR triggered by UJT, SCR ratings, voltage ratings, current ratings, di by dt ratings, advantages of SCR as a switch, gate turn off SCR, comparison between GTO SCR and SCR. We discussed about the diac, triac, uh, insulated gate, bipolar transistor, necessary of commutation, commutation schemes of SCR, and applications of SCR. So here in this, this is the total chapter of power electronics devices. So in this class, we discussed completely about the class C and class F's circuit diagrams, working and waveforms. Now here we have the few quiz questions and a few frequently asked questions. Now in next class we are going to discuss about the converters. So the converters means it converts AC to DC power. So this is the class today. Thank you.